To SFPE's Perspective Series webinar. What is linear heat detection? Is it right for your application? This is Chris Jelenowitz, SFPE's Technical Director, and I will be moderating today's webinar. Today's webinar is sponsored by Protectowire Fire Systems. Today's speakers are John Walling and Brenton Harris. John is the current president of Protectowire Fire Systems. With over 30 years of domestic and international fire protection industry experience, John has extensive knowledge about the design and installation of linear heat detectors within special hazards. As the former vice president of sales, John helped establish one of the most recognizable fire protection brands in the industry with a distribution network that spans the globe. John is a long-standing member of the National Fire Protection Association and the Society of Fire Protection Engineers. Brenton Harris is the Director of Sales at Protectowire Fire Systems and a frequent speaker at industry events. One of his main focuses is to provide educational trainings to the fire protection community both nationally and internationally. When he is not traveling, Brenton provides technical sales support to both engineers and end users as well as distributors. Prior to joining Protectowire, he spent almost 10 years in China working at both System Sensor as well as a private quality control company. Brenton is a member of the National Fire Protection Association and the Society of Fire Protection Engineers. So with that being said, welcome.
Thanks very much, Chris. It's a pleasure to be working with the SFPE once again. In today's agenda, we're going to be talking about digital linear heat detectors, their construction and operation, proper installation and testing, determining if LHD is the right fit for you, and question and answer wrap up at the end of the program. To understand the technology, it is important to demonstrate how the linear heat detector, or commonly phrased as LHD, is made and constructed. What is digital linear heat detector? It can best be described as a continuous run of heat detectors. It is a detector anywhere along its length. The sensor cable is comprised of two conductors, but both individually insulated by a heat-sensitive polymer. With Protectowire control gear, zones can be up to 10,000 feet or over 3,000 meters. Now we're going to talk about digital linear heat detector construction. The digital linear heat detector is constructed of a twisted pair of spring steel conductors, coated with a heat-sensitive polymer designed to soften at a specific temperature. When the ambient temperature meets or exceeds the detector's fixed temperature, the heat-sensitive polymer weakens, allowing the twisted spring steel conductors to make contact, initiating an electrical short, resulting in the monitoring device receiving it as an alarm condition. Now we'll talk about digital linear heat detector operation. What you see on the screen is three graphics showing the different states of operation of the detector itself. In the first graphic, we're showing a closed loop circuit which is monitored by the inline resistor. So the current flow going through the resistor shows the control panel or monitoring device that the circuit is intact. The second graphic shows a break. In the case of an open circuit, current flow stops and the monitoring device shows this as a trouble state or condition. The last graphic shows a short caused by heat above a preset threshold, indicates an alarm. As we mentioned before, when in a heated condition, the polymers melt, the two wires touch, and the short is seen by the monitoring device as an alarm condition. Digital linear heat detection. This technology does not require a proprietary interface unit. The detector is a contact device, as a matter of fact is listed as an open contact device. Calibration is not necessary for ambient temperature changes. Alarm point location is available. Non-restorable detector. Length per zone up to 10,000 feet, 3,048 meters. It's easy to splice. Maintenance and testing is very simple, as provided and required by NFPA 2016, Section 14. Fixed temperature, non-restorable line type, digital. Heat tests shall not be performed. Functionality shall be tested mechanically and electrically. Loop resistance shall be measured and recorded. Changes from acceptance test shall be investigated. Confirmed temperature initiation, or CTI Series LHD, is a new technology in the LHD market. Although it appears to be the same construction as regular digital LHD, it is made from different materials. The CTI Series digital linear heat detector is constructed of a twisted pair of dissimilar metal spring conductors, copper-coated and Constantan, coated with a heat-sensitive polymer designed to soften at a specific temperature. CTI Series Technology. We have not shown the normal condition with just the green LED on. The first graphic shows a broken wire or an open condition, which is similar to a regular standard digital. The differentiator for this particular product is the middle and the last graphic. The middle graphic shows a cold short, or something that might be caused by physical damage. The two wires have come into contact, but the module does not see that as an alarm condition. It only sees it as a short fault because there isn't enough heat present. In the last graphic, we show actual heat being impinged on the detector. The two wires are touching, the polymer is melted, and the panel sees that, or the control module sees that as an alarm condition. Digital thermocouple technology offers short circuit discrimination. Mechanical damage, a short at ambient temperature, creates a short fault or a trouble condition, not an alarm. Heat actuation, detector reaches or exceeds its fixed temperature, will render an alarm. The module is a 4-wire device. It's compatible with any fire alarm control panel. Calibration is not necessary for ambient temperature changes. Alarm point location and temperature confirmation are provided as standard features. It's non-restorable detector, and the lengths per zone can be up to 4,000 feet or 1,220 meters. And again, it's easy to splice. As far as test methods and inspection, we still use the same chart, NFPA 72, 2016, Table 14422. Heat tests shall not be performed. Functionality shall be tested mechanically and electrically. Loop resistance shall be measured and recorded. Changes from acceptance test shall be investigated. Proper installation and testing. The system designer has to be able to identify, and the installer has to be able to identify the product that he's working with, or the LHD type or model. So you'll see that on the LHD you have these markings: the manufacturer product identification, factory mutual approval mark, the jacket type, in this case it's EPC, which is a PVC jacket, and the activation temperature in Fahrenheit and also in Celsius. On the second line we have the Underwriters Laboratories listing mark and category, do not paint required by listings for all heat detectors, traceable manufacturer's lot number, and the incremental footage mark. Listed spacings. All heat detectors and smoke detectors have listed spacings to assist the designer in properly applying the product. This chart shows the different jackets for our digital LHD. It also shows the different temperatures that we offer. If you follow along to the first one, that says EPC and 135 degree, and of course we have in there that it's not available because we do not make the 135 in an EPC jacket. If you down one row, you'll see that it's made in an XLT jacket, which is good to 60 below. And the listed spacing at FM is 30 feet on centers, and of course at UL, 50 feet on centers. We've shown those values in metric, just slightly below that. If you follow along on this particular slide and on this chart, you'll see that we get over all the way up to 356. The 356 is listed and approved by FM for proximity detection. In other words, you put this particular detector on the apparatus you're trying to protect. For instance, transformers or conveyors. UL has given it a listed spacing of 50 feet for open area. One of the more important features of digital LHD is that we have the ability to pinpoint the exact location of the fire or overheat condition. This is called alarm point location. And due to the high resistance of the conductors, we can accurately measure the resistance from the starting point to where the fire is. As you can see on the line, Protectowire has an approximate resistance of 0.185 ohms per foot, 5.4 feet for every ohm, or 0.607 ohms per meter, or 1.64 meters per every ohm. This resistance is easily measured to determine the alarm point location. Installation guidelines for LHD. Consult with the authority having jurisdiction, or better known as the AHJ. Follow all applicable codes and standards. Follow recommendations of manufacturer's operation, installation, and maintenance manual. Recommended junction and end line boxes only. All LHD box penetrations shall use SR 502 strain relief connectors. Use of wire nuts or non-recommended products is considered improper installation. Detector wiring. This slide shows a Class A wiring scheme, and you'll notice on the left-hand box at the very top the conduit from the control panel. The wires are coming in, the interposing cable, and being connected on what we call a PWSC inside the box. I'll also point out that those are compression fittings. They're not terminal screws. As you all know, the LHD is made from steel conductors, and if you try to wrap it around a terminal screw, it will not stay on. So everything we do with LHD, digital LHD, is done with compression fittings. Coming out of the other side of the PWSC, you'll notice that it changes the Protectowire, then goes through the SR502 strain relief connector. That strain relief connector prevents it from being pinched and also seals the box from water penetration. The loop carries on until you get to the junction box at the end of the loop, where you transfer back to interposing cable using the same PWSC and the conduit going back to the control panel in a Class A configuration. This graphic shows a Class B wiring scheme, which looks very similar to the Class A with one difference. We're still coming from the control panel. We're using the interposing cable going into the junction box to the PWSC, coming out the other side of the compression fittings of the PWSC, and then through the SR502 strain relief connector, out into the field in the detection zone, and then back into the junction box. But instead of going back to the panel, we put the end-line resistor to condition the circuit and monitor it. LHD detector location on smooth ceilings. On smooth ceilings, the distance between parallel detector runs shall not exceed the maximum listed spacing. There shall be a detector run within a distance of 1/2 the listed spacing measured at a right angle from all walls or partitions that extend to within top 15% of the ceiling height, as shown in the illustration. This illustration also shows the FM spacing of 30 feet, and that 30 feet can be applied at a 10-foot level. LHD detector location on solid joist ceiling installations. With open joists or other similar structures, heat travels freely down the joist channels. However, heat has trouble spreading across the joists, so the distance in this direction must be reduced. The LHD shall be mounted on the bottom of the joists, and the spacing of the detector on all runs measured at right angles parallel to the joist shall not exceed 50% of the smooth ceiling spacing. On runs that parallel both joists and walls, the spacing shall not exceed 25%. LHD detector location on solid beam ceiling installations. In the case of beam construction, where the beams are 4 inches, 100 millimeters or less in depth, the ceiling shall be treated the same as a smooth ceiling. If the beams project more than 4 inches, 100 millimeters below the ceiling, The spacing at right angles to the direction of beam travel shall not exceed 2/3 of the smooth ceiling spacing. Where the beams project more than 18 inches, 46 centimeters below the ceiling, and are spaced more than 8 feet, or 2.4 meters on center, each bay formed by the beams shall be treated as a separate area requiring detector coverage. LHD detector location on slope ceilings or shed installations. In areas having sloped or a peaked ceiling, at least one line of Protectowire, or LHD, must be located at or within 3 feet, 0.9 meters, measured horizontally from the peak, but not closer than 4 inches, 10 centimeters, vertically to the peak. The spacing of additional runs of Protectowire, if any, should be based on the horizontal distance projected down from the ceiling in accordance with the type of ceiling construction. LHD installation guidelines. Avoid mechanical stress of detector, pinching, crushing, or bending. All of those operations should be done with the fingers and hands and not use any kind of tools. Do not make 90-degree bends. All bends made by hand with a minimum of a 2.5 inch radius. Use recommended fasteners only. Do not over-tighten fasteners. Do not paint detector UL and an FM requirement. Allow for expansion and contraction due to temperature. The detector should be loose in the fitting. Test LHD prior to installation as per manufacturer's instructions, and do not store the LHD above recommended ambient temperatures. NFPA 72 requires that all heat detectors spacings be reduced based on ceiling height. This chart shows the reductions and the percentage reductions that can be applied. Because we have FM and UL, and those spacings are different, again, FM is 30 feet on centers for most detectors, and UL is 50 feet on centers for most detectors, they have to be applied to this chart. At 10 feet, we can use the listed spacing, FM 30, UL 50. But as we go higher, and the ceiling height goes up to 28 to 30 feet, we can only use 34%. The spacing has to be reduced down to 17 feet for UL and roughly 10 feet for FM. Digital LHD models and reduced spacing. Most of you will have noticed that on the previous slide, the chart only went to 30 feet. But there are many buildings and ceilings out there that are much higher than 30 feet. And NFPA 72 put in this clause a few years ago, and it deals with ceiling height. 176352 states, the minimum spacing of heat detectors shall not be required to be less than 0.4 times the ceiling height. If you took a 100-foot building and a 50-foot listed spacing, you would reduce it down to 40 feet on centers. And that 4% is of the 100, not of the 50-foot spacing. The justification for this is in the appendix. I'm not going to read the whole thing, but the width of uniform temperature of the plume when it impinges on the ceiling is approximately 0.4 times the height above the fire. So reducing the spacing below this level will not increase the response time. LHD installation guidelines, thermal coefficient of expansion. One of the things the designers and the installers have to consider is that this product is made from steel wire, which expands and contracts with temperature. In many cases, and for instance in the case of a freezer complex, they may be installing the detector at 70 degrees or even higher. But once that building is enclosed and ready to go, they start turning on the cooling units, and it may go down as low as 20 or 30 below, which will cause the detector to contract. This chart basically gives the designer a guideline as to how much slack to leave in the detector so that when it does go from one temperature to a much, much lower temperature, that slack will be taken up. Testing digital linear heat detectors. NFPA 72 is very clear on how to test restorable detectors and non-restorable detectors. And the basic difference is, with fixed temperature restorable or rate of rise, then a heat test shall be performed of each and every detector, which can be very laborious and time consuming. With fixed temperature non-restorable line type, Protectowire or digital LHD, the heat test does not have to be performed. You only functionally test it by shorting it out at the end of the loop to make sure it goes into alarm, and you record the resistance to make sure it's not appreciably different from the acceptance test. I will now turn this portion of the presentation over to Brenton Harris.
Good morning, everyone, and thank you, John, for that introduction. What we're going to cover next is determining if linear heat detection is the right fit for your application. Here are 5 quick and simple questions that can help determine if digital linear heat detection should be considered for your application. Question 1. What type of application are you protecting? Protectowire can predominantly be found in either commercial or industrial applications, although there are some limited residential applications where you'll find Protectowire. An example of this would be when Protectowire is placed in an attic. Following up on the commercial or industrial applications, you need to consider what type of environmental conditions are present. We offer very detailed chemical resistance charts for all of our detector jackets on our website. The next question, question number 2, seems simple, but it's very important. Interior versus exterior applications changes the jacketing material on the detector. Interior applications can use a UV stabilized outer jacket, like our EPC jacket, while outdoor applications should use a naturally UV resistant fluoropolymer, like our XCR jacket. As John touched on earlier, the jacket is the detector's protection from the local environment, so it must be chosen carefully. Moving on, is your application within a classified area? Digital linear heat detection can be made intrinsically safe through the use of ISBs or intrinsic safety barriers. Keep in mind, this is very different from explosion-proof detectors. There is no explosion-proof Protectowire. Rather, the use of intrinsic safety barriers enables the standard detector to be located within a classified area. With this type of application, the properly rated control equipment and relevant FM-approved control drawings must be followed and used. Our last question asks, what is the maximum ambient temperature? Given the detector's fixed activation temperature, knowing the maximum ambient temperature allows you to determine the correct fixed temperature detector for your environment. Please note that these are not all the questions that must be asked, but rather a quick guide that can walk you through determining if linear heat detection should be considered for your application. To further the questions about application that we asked on our previous slide, please find this feature chart. This includes all of our linear heat detection products. This chart is a summary of the questions we covered on the previous slide. Something worth noting is that this chart is available on our website for future use, as it's really a great tool for assisting in determining the correct jacket and temperature requirements for your linear heat detection. We'll now move into discussing some of the most common applications that employ linear heat detection. There are considerably more applications than those listed on this slide, but for the purpose of this webinar, we're going to focus on power generation, petrochemical storage, warehousing, transportation, self-storage, 2 new applications where we're seeing a lot of growth, and we'll finish up with some unique applications. Cable tray protection is a tried and proven application for digital linear heat detection. The long, extended runs of proximity detection allow for early hotspot identification. especially in places with limited access points or infrequent use. Pictured here, the linear detector is placed in a sinusoidal, basically an S, pattern, enabling exposure to each of the cables in the tray. There are also applications where the linear heat detector is installed on or near a single cable. In that case, the detector is installed in a straight line, paralleling the other cable. A challenge found in protecting cable trays can be EMI and RFI interference. It's important to note that Protectowire offers both control panels and interface modules that employ hardware and software filters to minimize the effects associated with EMI or RFI. Heat detection on conveyor belts is another strong application for linear heat detection. Again, the detector can be placed directly on the hazard, offering proximity detection. The primary goal of detection on conveyors is to enable quick detection for any type of operational failure. This could be a bearing failure, friction from belt slippage, a roller locks up, or anything similar. The robust design of the detector allows for an extended service life even in the harshest of environments. This application is a perfect fit for our CTI Series linear heat detector because should there be any physical damage to the detector, it will not give you a false alarm. This assures that your deluge system or any other type of suppression system only activates on confirmed temperature initiation. Lastly, it's not uncommon for underground conveyors to be located in classified areas, Class 1, Division 1, or the ATEX equivalent. Remember that these classified areas can be protected with digital linear heat detection when employing an intrinsic safety barrier. Another very popular application for digital linear heat detection within the power gen industry is transformers. The digital linear heat detector can be placed directly on the transformer using specific attachment devices to allow for installations without drilling into the transformer. An important note, though, with this type of installation style is that you should not fully encircle the transformer. If you look at the illustration on the right side of your screen, you will see the detector almost encircles the transformer and then returns back to the start. The purpose behind not completely encircling the transformer is to limit EMI and RFI interference. The second means of protecting a transformer is to place the detector on the deluge piping around the top of the transformer. Prior to using this installation technique, however, you will want to check or verify with your local AHJ, authority having jurisdiction, to verify if they'll allow the detector to be placed on the sprinkler or deluge piping. The interpretation of NFPA 13 can vary significantly with each jurisdiction. An application that we have seen gain momentum within the last few years has been electrical compartments and vehicle systems. As the price of all vehicles, whether it's a small hybrid or a massive earth mover, continues to rise, so do the challenges of protecting their electrical systems. The versatility and flexibility of digital linear heat detection allows the detector to be placed in and weaved around tight spaces to provide the necessary proximity detection within engine compartments. Further, all Protectowire interface modules can run on either 12 or 24 volts, making them compatible with existing systems. When necessary, an existing third-party converter can be used. An example of this would be when you convert the interface module's relay contacts or 4 to 20 milliamp outputs to the CAN protocol, enabling simple integration into an existing vehicle system. Cooling towers are basically a swamp and are another popular application for digital linear heat detection. The high-risk items within a cooling tower are the fan motor and gearbox. There are limited detection technologies or even products that can survive within an operational cooling tower. Optional, but highly recommended, is the additional coverage placed in and around the wood fill. While the tower is operational, the wood is soaked and should not ignite. But if the tower is taken offline for maintenance or some other reason, the wood fill dries out and is highly combustible. Fuel and chemical storage is another common application for linear heat detection. Protectowire can be used on open-top floating roof tanks, fixed-top floating roof tanks, and fixed roof tanks. For open-top floating tanks, pictured in the illustration here on the left, the linear heat detector should be placed below the secondary seal, just above the primary seal, as this is most likely where the flammable vapors will collect. This can be difficult to access, however, and if that's the case, the detector should then be placed on the foam dam just outside of the secondary seal. Fixed-top floating roof tanks and fixed roof tanks are often protected the same way, despite the fact that there's a floating roof enclosed within the tank. For these tanks, the most common location for detection is around and over any of the vents within the tank. Should the air inside become hot, this will activate the detector and initiate an alarm. Regardless of the tank type, many of these locations are classified, so the use of intrinsic safety barriers may be necessary. Refrigerated and warehouse storage is another popular application for digital linear heat detection. For this application, we typically recommend a hybrid system. Standard digital linear heat detection, where the conductors are the same metal, this can be used in the ceiling. For any and all rack installations, we recommend our CTI Series detector. Any detector installed within a rack has a higher risk of damage. With our CTI detector, damage will only initiate a trouble condition, not an alarm. The detector should be located on the back of the load beam, hidden from forklifts if and when possible. We do not recommend putting the detector on in-rack sprinklers. Many of these warehouses use double interlocked pre-action systems. And if a pallet or box or something similar falls out of a rack and hits the sprinkler pipe and damages a standard digital linear heat detector, you would have a short on your detector and a low air condition in your pipes, causing water to flow despite there being no fire. This is why I'm emphasizing two things in this slide. If you want to use standard linear heat detection, do not put it on the pipes, put it on the back of the load beam. And the second is that you should use the CTI series to assure that you do not flow any water until there is actually heat present. Finally, if you're unsure where to put the linear detector, FM datasheet 8-29 suggests one run of linear detection for each row of in-rack sprinklers. Aircraft hangars are another common application for linear heat detection. Given the often varying ceiling heights, you should consult NFPA's reduced spacing chart, which covers up to a 30-foot ceiling height, or NFPA's listed spacing exemption rule, the 0.4 times the ceiling height, but you cannot exceed the maximum listed spacing. Both of these were covered earlier by John today. If you design or install a Class B configuration, we recommend locating your end-of-the-line box approximately 8 to 10 feet off the floor height. This will enable whomever is servicing or testing the system to do all the necessary testing with only a small step ladder, rather than requiring a scissor lift to open up a junction box 30, 50, maybe 80 feet in the air. Alternatively, the designer or installer may want to consider wiring in a Class A configuration, allowing the system testing and inspections to be completed back at the control panel. This is another ideal application for the CTI series detector, as hangars can be protected by high expansion foam systems, and you want to be 100% sure there is a fire or a hotspot prior to discharging a suppression system within a hangar. Tunnels are a perfect application for digital linear heat detection. The often long runs can be easily covered by the extended zone lengths offered with linear heat detection. We recommend supporting the detector with a mounting accessory every 5 feet. Given the potential difficulty in mounting in tunnels, this can be an application for messenger wire. Messenger wire is a high tensile strength wire that can be connected using turnbuckles. This enables you to place your mounting supports 30 to 50 feet apart rather than every 5 feet. There is more information about messenger wire and its applications located on our website. But lastly, I'd like to talk about NFPA 502, which requires you to identify a tunnel hotspot within 50 feet. With the resistance value calculations or alarm point location meters offered in the control equipment, linear heat detection can easily comply with with NFPA 502's requirement. Self-storage facilities demonstrate the versatility of digital linear heat detection. Running the detector above each unit allows for zero privacy invasion when the annual testing and commissioning is performed. By shorting the detector at the end of the line, you can be assured it is operational everywhere along its length. Further, if these facilities are not temperature controlled, the detector is immune to rapid temperature changes. Finally, if or when there is a fire, the alarm point location will tell first responders or owners exactly which units are experiencing the overheat. Earlier, I mentioned two new applications where we are seeing a lot of activity. New construction and renovation is one of these applications. We've seen a recent increase in the use of linear heat detection, specifically our CTI series, as temporary detection while a building is being renovated. Typically, many of the spot detectors are removed during the renovation process, but the building fire alarm control panel remains active. Our interface module is connected to the building control panel, and then the linear heat detector is laced throughout the facility. This enables 24-hour fire detection in a facility where some or all of the permanent system has been temporarily taken offline. The reason the CTI series is popular for this particular application is because of its short circuit discrimination. Damage to this detector does not cause an alarm condition. There's not a lot of information about temporary detection in NFPA 241, but most of the AHJs we've encountered so far have been very receptive to this approach. Protecting solar panels is the second new application where we have seen significant activity. While solar panels themselves rarely fail, external environmental factors have a significant impact on the reliability of solar panel arrays. Whether it's age, maintenance operations, roof debris, animal nests, poor electrical work, or physical damage to the panels can cause them to overheat. For this application, the linear heat detector is typically placed on the highest longitudinal support beam, as you can see in the illustration on the left side of your screen. Once more, for this application, we recommend the CTI series, and this is for two reasons. One, physical damage to the detector will not initiate a false alarm, it will only issue a trouble condition. And two, many of the solar panel installations are retrofit onto buildings that already have an existing fire alarm control panel. The CTM 530 interface module is a simple means of integrating linear heat detection into an active system. We also recommend that some kind of enunciation or zone map is completed and recorded. This allows building owners and first responders to immediately identify the location of the hotspot or failing panel. This is a picture of a vineyard in France where the detector is used strictly as detection. While it's common for the linear detector to be paired with some type of suppression system, there are also plenty of applications where the linear heat detector is the only system component. The goal of the perimeter fire protection is to detect a forest fire and alert the appropriate personnel so they can respond appropriately. Given the linear heat detector is a fixed temperature detector, the seasonal temperature changes are not a factor in this application. Our last slide truly demonstrates the versatility of digital linear heat detection. As you can see, the linear heat detection is used in iconic landmarks, religious institutions, primarily because of the ease of annual testing and inspections within hard-to-access locations. Linear heat is also used to protect historic covered bridges and wooden rail trestles because it can withstand extremely harsh environments and severe operating temperatures. Linear heat can be found below subfloors, in concealed spaces, and within interstitial spacing, or basically the areas that are above a drop ceiling, because it provides continuous coverage anywhere along its length. It also makes complying with NFPA testing requirements very convenient, as you only have to access the end-of-the-line resistor and short the detector. The detector is employed in these unique applications for many of the same reasons that it's used in other places, whether it's the extended service life, reliable performance, ability to offer proximity detection, and the fact that complying with NFPA testing requirements is easy. This concludes our webinar presentation. At this point in time, I'd like to turn it back over to the SFPE for the live Q&A. Thank you.
Thanks for a great presentation. We do have some time to take questions. So let's get started. Is the CTI Series and CTM module a standalone system?
No, the CTM 530 interface module and the CTI Series linear heat detector are not a standalone system. Our UL listing and FM approval require two things. One, that the CTM module be connected to a listed or approved fire alarm control panel via relay contacts. And two, our listings and approval require that the CTM module and CTI Series linear heat detector be used together.
Can I combine the standard digital LHD with CTI in the same zone? Or splice together?
The short answer to this question is no, you cannot. It refers to the previous question where UL and FM requires that the CTI series, the CTM 530 and the CTI series detector be used in conjunction with each other. The CTI uses different conductors than the regular standard digital PHSC Protectowire, and they have different resistance values. The Protectowire company recommends that you do not mix and match. The CTI series has special features, short circuit discrimination, which the PHSC does not. If you mix them on the same circuit, you're going to get all kinds of different results. So to answer the question is, they should not be mixed.
What is the life expectancy of linear heat detectors?
Technically, no specific service life for Protectowire linear heat detector exists, either by code or by recommendation. The service life is a function of environmental conditions that it's exposed to. For instance, chemicals, vibration or abrasion, support spacing and mounting accessories, physical factors, and as previously discussed, jackets are the protection for the detector and should be chosen correctly for the environment. Based on feedback from customers, our own use and testing, properly installed and serviced Protectowire will operate for decades.
How many splices can I put onto a linear heat detector zone?
Similar to the question about life expectancy, there is no definitive answer when it comes to how many splices can I place into a linear heat detector zone. The suggestion here would be use good engineering practice. As a manufacturer, we recommend as few splices as possible. Each splice placed in the detector creates a chance for loose connections, maybe ground faults, water damage, or any other additional problems. Given the harsh environments in which our detectors are used, if the splicing is excessive, that portion of the linear heat detector should be replaced. This concludes the webinar. Thank you for attending. If you do have any additional questions, please contact us at info@Protectowire, info@protectowire.com.